So I don't know how many of you really have looked at the webpage to see how this program had gone. So this has been a 2-month-long program called Dynamics of Complex Systems, which we have been having for the last 4 years. So we had applied for a 4-year cycle and it was approved. So every year we have one theme. All this is there, but I'm just reminding you. And on that theme, we have a summer school and a discussion meeting. So this year we chose this theme, as you know, and from May 15th to 31st, we had a summer school where it was mostly attended by students, either postgraduate or PhD, postdocs, even early career scientists. There we had only teaching, like teaching of different methods that are used in this area. For example, we had a 4-day module on networks. We had a 2-day module on genetic algorithm optimization. We had a 3-day module on game theory. And then we had a 2 or 3 days, I think 3 days module on agent-based modeling. And the last one was a 3-day module on time series analysis. This is the first time we have done anything like this. And I think this is the first time we have done in India anything like this. I don't know about other places. And we ourselves learned how to go about it if we ever do it again. And if any of you are organizing, we will be happy to share our experience, what to do and what not to do. That was very successful, as the feedback told us. It was really very nice. People spent a lot of effort. Then we had a period from 1st of July to 1st of June to 8th of July, where three people were selected from that among the participants of the summer school. Not necessarily they were the best students, but who we thought would be able to get some, will gain from staying here longer, and they were called long-term participants. And then the last bit is this 5-day program where we have more of early career faculty and some senior professors and that to discuss more about the problems. Now today what we have here is those 3 students. One of them is a early career faculty from, you can see, from Ramjas College in Delhi. The second one is, he's just finished his BSMS from ISER Mohali. And the third one is still doing MA in economics in Ashoka University. So we chose people from different backgrounds, and we were 3 people who stayed here. Amit, anyway, is a faculty, so he was here. I had continued staying these last 2 months, and we also invited Niban Chakrabarti to come and stay here, which was a very good thing to do because the students really gained from his stay. So these 3 people will speak of whatever they are going to do. Please understand that some of them have really just started even knowing how to go about it. So it's not really a presentation of big results and things like that, but more to say what they have done. So, and please, they should talk to you after the presentation during tea time and all that, and discuss with you what they can do more and things like that. So that's how it is. Thank you.
Good morning to all of you. First of all, I would like to thank the organizers for giving me an opportunity to work as the long-term research participants here in ICTS. And this work has been carried out under the mentorship of Professor Anirban Chakrabarti, JNU. And we have carried out the time series analysis of the terrorist events in the global terrorist database. And the motivation of our study is that apart from the social scientists, physicists and data scientists have all tried to perform in-depth studies and provide mathematical models, statistics and time series analysis of the empirical data. And in the social physics, the social interactions or activities can be modeled as time series where intriguing patterns in their collective behavior, coherence, synchronization, etc. are often seen. And we can model these patterns in the correlation of the activities using nonlinear dynamical models and the time series method. And social physics is marked by the belief that the large-scale statistical measurement of social variables reveals underlying relational patterns that can be explained by the theories and laws found in natural sciences and physics in particular. So in this work, we aggregate the terrorist antisocial events over the time from the global terrorism database, and we study the temporal evolution of the terrorist events across the globe. Now, this global terrorism database is maintained by the National Consortium for the Study of the Terrorism and Response to the Terrorism, START, in the United States. And the database was built on unclassified source material publicly available in media, digital news archive, books, journals, and some legal documents. And this contains 1,70,350 terrorist events reported for a period of 46 years from 1970 to 2016, excluding the 1993 because due to non-availability of data for this period. And this dataset includes 135 variables in the GTD ID as GTD ID, date of incident, incident location, incident information, weapon information, attack information, target or victim information, preparator information, and other data, weapon information, casualty information, consequences, kidnapping hostage, taking information, and other informations. So the snapshot of the database is like that, and this data was too complex and it was filtered by Sharik Hussain and Kiran Sharma in JNU, and they have collaborated with us in the database. So now this is the time evolution of the number of the terrorist events from this period, and we can see that there is a this black inherent line shows the trend, that there is a trend in the time series. So therefore, and when we plotted the PDF, so in the generally in the probability density function, they are too noisy, especially towards the tails. So we plot the complementary cumulative density function as it reduces the noise content and makes the information contained by the signal clearer. So now we fit this trend by the polynomial of the order of the degree 10, and then divide the original series by computed trend. So in this manner, we detrend the time series, and this is the resulting detrended time series. And we can see that the yellow, there is a flat line, so it shows that it has been detrended, and quite we can assume that it is weakly stationary. So now, as the number of the news entries and per day is a stochastic variable, so we often see a burst of activities in GTD, and due to large inter-day fluctuations in the number of reports and bursty nature, the CCDF shows a broad distribution. Now, as a physicist, we have looked at the Gutenberg-Richter Law, which is for the earthquake, and where it gives the relationship between the magnitude and the total number of the earthquakes in any given region and time period of at least that magnitude. So here, this is given by this formula. This is an empirical formula, and n is the number of events having a magnitude greater than or equal to m, where m is the magnitude. A is the productivity, is a measure of the seismicity, and B value serves as the kind of the tectonic parameter. Its value is 1 for earthquakes, and it ranges with the different variables, and it follows this law, this behavior. Since m is proportional to the logarithm of energy, so the Gutenberg-Richter law is a power law, and approximately it fits linear. So when we analyzed the GTD event time series, we found this similar behavior as for the earthquakes. Now, after the earthquakes, so there are the aftershocks, because the larger earthquakes can have hundreds or thousands of the instrumentally detectable aftershocks, which steadily decreases in magnitude and frequency according to the known laws. And there is a Omori Law in 1894, which shows the frequency of the aftershock decreases roughly with the reciprocal of the time after the main shock. And here K and C are the constants, which varies between earthquake sequences. Then there was a modified version of the Omori laws by Utsu in 1961. And here we have the third constant, which modifies the decay rate and typically falls in this range for the earthquake. And we to simplify, to use the Omori law, we integrate equation number 2 between 0 and t. So we find the cumulative number of aftershocks observed until time t after the main earthquake shock. And for earthquakes, its value lies between this range. Now, for the GTD time series, we found the similar that it follows the Omori's laws with the parameter p.3, and now in so these are the okay. So we also have looked at the extreme values by by considering that extreme events are rare in nature as well as in social phenomena. So we study the recurrence interval, which is the interval between the two consecutive extreme events, and we compute the CCDF of the events, and we see that it fits well by the stressed potential and as the quantile increases, then distribution becomes fatter. That is, lower recurrence time intervals occur less frequently. So at higher values of Q, there are fewer extreme events and they are spread apart. So in this paper, the Professor Anirban Chakravarti and all, they have studied the extreme events and copulas in the financial markets. So now we have studied this in the social phenomena of these activities. So now, we also study the nonlinear dynamics approach to the GTD database, and we know that fractal, we have seen this is the Mandelbrot set, and fractal is a structure which is composed of the parts, which is in some sense similar to the whole structure. And this is a typical example of the Koch curve, how it forms on the basis of the self-similarities. And this is a fractal which models the surface of the mountain. We can have the different type of the fractals based on the type of the self-similarity. So the multifractals are multifractal is a system which is the generalization of the fractal system in which the single exponent of the fractal dimension is not enough to describe its dynamics. And the example of the multifractal systems are human heartbeat dynamics, then geophysics time series, fully developed turbulence, real world scenes, and sun's magnetic field time series, and the stock market time series. So, and it shows it behaves a power law. I will explain that how, where from it is coming. Now, we have used the multifractal detrended fluctuation analysis method to study these events, and we consider a time series xk. And there are 4 steps in this method. First, we calculate the profile, and then we convert this time series, the noise or the random times, any time series into the random walk like time series, and then we divide the profile into ns non-overlapping segments of equal length. Since the length of the series is not often a multiple of the considered time scale s, so a short part of this series may remain. So for that we do the same procedure from the opposite end, and we obtain the 2ns segments. Now this is the way we have taken the 3 type of the time series: white noise, monofractal time series, and multifractal time series. And in the first step, we convert this as the random walk like time series, and then in the next step, we calculate the local trends for all these 2ns segments by the least square fitting of this series, and then find the variance. And so it is y nu I is the fitting polynomial in the segment nu, and we can fit the linear, quadratic, cubic, or higher order polynomials in the fitting procedure. And since the detrending is done by subtracting the polynomial fit from the profile, so we can have the different order MF-DFA in the analysis. And this is the way that so this is the linear detrended of this random walk time series, and then we find the average of that. When we average over all segments, then we obtain the Q order fluctuation function. And and then from this fluctuation shows a power law, which describe the scaling behavior of the fluctuation on log plots. And if there are long range, then it follows a power law. And we can see for the different values of Q, we have the different exponents. So here this SQ is known as the generalized Hurst exponent. and which is related with the classical multifractal scaling exponent by this relation. And we also computed the Hurst exponent of this terrorist event time series by using the Rescaled-Range analysis method. And here the Hurst exponent, as we know that it is a popular measure of the long-term memory in the time series, and its value from 0 to 0.5, it indicates a time series with the anti-persistence behavior, and if it is higher than 0.5, then it indicates a time series with the persistence behavior, or if it is 0.5, then it shows that completely uncorrelated time series. And we found this, the Hurst exponent comes out to be 0.7794. That means this shows that there is a long-term memory in the terrorist event time series. Then we compute the the behavior of the generalized. Okay, this Hurst exponent. So earlier we found the Hurst exponent by using the rescaled-range analysis method. Now we also computed the value of the Hurst exponent by using the DFA method, detrending fluctuation analysis method, and we found the similar results. Just to cross-check, the generalized Hurst exponent shows. So this is almost flat. So this is for the white noise. This is for the monofractal time series, and this nonlinear behavior of the generalized Hurst exponents indicates that there is a multifractality, the indication of the multifractality in the event time series. And from the generalized spectrum of the generalized Hurst exponent, we calculate the singularity strength alpha. Alpha is also known as the Holder's exponent, given by this relation, which is related with the HQ. And we can see that this the spectrum of this multifractality is, so we can see that, so we calculate the strength of the multifractality delta alpha by alpha maximum minus alpha minimum, and we find the spectrum for the different system for the white noise monofractal. So this is for the white noise, this is for the monofractal, and this is for the GTD data. And we find that this comes out to be 0.75, so which is much higher, which indicates that the global terrorism database time series exhibit the multifractal properties in it. So now we, in conclusion, concluding remarks, we have analyzed the time series from the period of 1970 to 2016, and we find that they have the interesting statistical regularities and correlations, and we've tried to verify the Omori's laws and Gutenberg-Richter law and studied the recurrence interval analysis, and then we find that these time series exhibit the multifractality. And if there is the existence of the multifractality in the time series, then it may help us to identify and explain the underlying physical mechanisms that dominate and govern the dynamics of the system. So these are the references. So this is a continuation of the already work which has been, so using network analysis and then data science approach, and network analysis of this thing. Now we are focusing on the time series analysis of this time series. And now I would like to thank the Sharik and Kiran Sharma for the data collaboration, and Ashish and Rishidev for the discussion and critical inputs, and obviously Professor Somdatta ma'am and Amit sir for their support and encouragement. So thank you very much.
If there are questions, yes.
Thank you, but I think it was sort of expected. It was a good presentation. I have 3 points. So when you're talking about terrorist organizations and you're mapping this, right? Mm-hmm. The events. So the thing is that many groups merge across different times and then they bifurcate. For example, if I'm just taking Jabhat al-Nusra, they were known as Al-Qaeda in Iraq, then they split from ISIS, and then they made Jabhat al-Nusra. Then they were still with Al-Qaeda, then they merged, and then they changed it to Tariq-e-Sham, and then they merged with 5 other groups. So these groups merge and then change identity, the groups change. So how are you going to measure this? So the events that you're measuring, you can't just measure them as singular events because they are sometimes done as coordinated events, sometimes as singular events by particular groups. And apart from that, this is being done. So perhaps you could look at that. One thing you could do for this is there's a QDE international numbering system. So all the terrorist organizations and all the major entities have an international QDE identification number. So if you could match it with that and then go ahead with it, it could perhaps help. Second is that you were talking about the rate of decay, right? So I think that this would work only for the larger terrorist campaigns because if you're having singular events, then there can't really be a rate of decay. For instance, the Pulwama attack that I was talking about, that was a single event, but the current Taliban campaign, which is happening for the multiple bombings, that's a part of an announced campaign. So you can have a rate of decay, and they literally announce it that we're going to start from next week, and then they go on with it. I think if you're using that, you'll have to be a bit careful. Another thing that you would have to do with this is the time frequency. You can match it with that because these campaigns that you have for which you would have the rate of decay, these are only known as the summer campaigns. So most of these groups do not act in winter times for certain reasons, and it's tougher and more difficult to get the people to work and all that. So they have certain winter campaigns are for shorter period, summer campaigns are for longer period. If you merge that with this, I think it would be of greater help. Because if suppose you're sending this data across to me, while the data, even I use the GTD data set, but I think using this across different groups would be something that's more useful rather than just saying that, okay, these are the number of attacks that happen.
Thank you. Sasi.
Okay. Yeah, no. So is it true that a major terrorist attack is followed by this aftershocks kind of small attacks? Is it true that?
No, actually, we have obtained the database of this time series. We were just trying to analyze that whether these time series events, whether they follows that, just to check it whether. And then we found that, okay, after that, when we plotted the distribution, then we find that, okay, it is following the similar behavior. So that is. Okay. Yeah.
As I understand, multifactorial is the property of set of points. If I have any set of points, whether it comes out of dynamics or not dynamics, I can always calculate different kinds of dimensions and all that. Just like if I have set of points, I can calculate mean, variance, and all sort of things. Now, can one really from multifractal exponents or whatever measure you take of multifractality, extract the dynamics? I mean, is there any example where that can be done, even for a very simple system? Can I write down the equations of motion by looking at multifractal exponent?
Not.
I'm just saying I'm not aware of it because in nonlinear dynamics there is a system called Rosler system. It's a very simple system. People have tried to extract out different exponents of the attractor, and from the attractor they have tried to find out whether you can write down the reverse engineer and find out the equation of motion of Rosler. Yes. Even that has not worked. So it would be great if that future objective could be achieved, but is there any precedence that it has been achieved?
Actually, the property of the multifractality, as I have shown you the human heartbeat dynamics, and there is a paper in the Nature which has published, and in which they have studied the normal heartbeat time series, which indicates the multifractal behavior, like the spectrum of the multifractality. And during the heart attack, when at that time the multifractality breaks down. So I have not done this thing, but maybe that there are some certain events where the multifractality is is breaking down during the extreme event or some. So that is my understanding of it. Any other question?
If there are no more questions, let us thank